Hey, AP Statistics, welcome to section 9.3, tests about a population mean. So we're going to get into significance tests for mu. In this section, you should end up being able to state and check the random 10% and normal/large sample conditions for performing a significance test about a population mean. Good news is those are the exact same as last chapter. Calculate the standardized test statistic and p-value for a test about a population mean. Perform a significance test about a population mean. Use a compass level to make a conclusion for a two-sided test about a population parameter, and interpret the power of a significance test and describe what factors affect the power of a test. So we'll get more into that. All right, so conditions for a significance test. We've got, these are pretty much the exact same as last chapter for the one sample t interval. So the one sample t-test, we need the random, data come from a random sample, 10% samples less than 10% of the population, and the normal/large sample. Either the population is normal, the sample size is large, so we can use CLT, or if we don't know, then we can graph our data and look and make sure it doesn't look super skewed or have any outliers, and kind of assume the population is somewhat normal. In that case, we can go on with T procedures. It's not enough to make a graph of the data on your calculator when assessing normality. You must sketch the graph. So you can't just look and say, I looked at my calculator. Actually, just sketch the graph on your paper and make an appropriate comment about that to receive credit. You don't have to draw more than one graph. A single graph will do. Just a nice quick sketch, get a few numbers on there. It doesn't have to be a work of art or anything. All right, so example problem. Here are the lifetimes in hours of the 15 deluxe AAA batteries from the company's simple random sample. Check if the conditions for performing a significance test are met. So random, check. These were a random sample. 10%, we'll assume that there are more than 150 batteries. And then the normal/large counts, large sample, we don't have the large sample. We're 15, we're below that. They're not told that the population distribution of lifetimes are normal. However, our data here doesn't show any strong skewness or outliers. We've got some data clustered in the middle, some data spread out. Don't get too freaked out that 2 points stacked up here. That doesn't mean that that's the most, the center of the data. We still have kind of a nice cluster in the middle, and so it's relatively spread out. It looks fine. All right, so carrying out our test for mu, we're going to calculate our standardized test statistic. This is, what would be our z-score minus our statistic minus parameter over our standard deviation of statistic. That's what we want to see, is how far from the expected is our result. So this would be ideal. In an ideal world, our test, if we had a null hypothesis that mu equals some number, our standardized test statistic would be to find our x bar, how far it is from that mu, and divide by sigma over root n. But, so that would be a z-score. It would be a number of standard deviations from the mean. It'd be the standard deviation of that statistic from the mean. However, in reality, because population standard deviation sigma is almost always unknown, we use the sample standard deviation S in its place. The resulting standardized test statistic has the standard error of x bar in the denominator, and then is denoted by t. So if you were somehow given sigma, this is what you would use. That's exceedingly rare, and so instead you will end up almost always using this instead, a t-test statistic where we do x bar minus mu, and since we're using s over root n, t is the better distribution to use to find how unlikely those results are. So when we perform an inference about a population mean using t distribution, the degrees of freedom is n-1, same as last chapter. So that t distribution is that symmetric single peak bell-shaped density curve, just like the normal distribution, just a little shorter and wider. Any t distribution is completely specified by its number of degrees of freedom. When performing an inference about a population mean based on a random sample of size n, when the population standard deviation sigma is unknown, we use a t distribution with degrees of freedom n-1. So we just see it here. It's a little bit flatter, a little bit wider. It gets closer as the degrees of freedom increases. As the degrees of freedom approaches infinite, or the population size, then we end up with a normal distribution. So that's just saying we're using a t distribution. T-distributions are similar in shape to the normal distribution. They're symmetric about 0, single peaked and bell-shaped area. Their density curves, area below them is 1. All kind of the same similar stuff. And the T-distributions have more variability than the standard normal distribution because T-distributions have more area in the tails. And this is all stuff that's kind of just a review of last chapter. We used the T-distribution for our confidence intervals. As the degrees of freedom increases, it approaches the normal distribution. So we can use table B to find a p-value from an appropriate t-distribution when performing a test about a population mean. So in the better batteries example, the mean was, the null hypothesis is that the mean equals 30. Alternative is the mean is greater than 30 because these batteries are better. That's what we're trying to find evidence for. So we have a sample statistic here, x bar minus that 30, and we divide that by the standard error. Ultimately, the standard deviation of the sample was 9.82 over square root of 15, and we get this 1.55, but that is a t-test statistic. Our degrees of freedom, since we had a sample of size 15, is 14. And so what we would look up in that row is the 14 row for the degrees of freedom. So the limitation of this table is it doesn't actually give us our exact p-value. I'll show you how to do that in the calculator as well. But if you use the table, what you can see in row 14, if you look for this 1.55, you won't see it, but you'll see it's between those two, right? In that row 14, you'll see a 1.345 and a 1.761. So it's somewhere in between there, somewhere between 5 and 10% for the tail probability. And so all we can get from our table is that p-value is somewhere between 5 and 10% or 10 and 5%. That's the best we can do with that. So it has its limitations for finding p-values. It gives an interval of possible p-values for a significance test. The table shows probabilities for only positive values of t. That's another downside of the table. To find a p-value for a negative value of t, we have to use the symmetry and say if we want to go below negative, we have to go figure out what the positive number is and go above it. And then the table does not have all the potential degrees in freedom. It goes from 1 to 30 and then starts skipping around. And so not ideal. Caution, if the degrees of freedom you need isn't provided in the table, then use the next smaller one that's available. And you can get away with that on the A/B test, though I will recommend that you use the calculator to do that. And we'll come back to that. Suppose you want to perform a test of the null hypothesis is 5 versus the alternative not equal to 5 at the 0.01 significance level. So that's how unlikely we want something to be. If it's less likely than that, we will reject the null hypothesis and accept the alternative and so on. A random sample of size 37 from the population of interest yields an x bar of 4.81 and a sample standard deviation of 0.365. Assume that the conditions for carrying out the test are met. Explain why the sample result gives some evidence for the alternative hypothesis, and then calculate the standardized test statistic and p-value. So for the first example, the reason that there's some evidence is because this x bar is not equal to 5. That's all it really takes. If we're trying to say that it's not 5, well, my sample mean is not 5. So there is some evidence, but is it significant evidence? And so that's where we actually need to calculate this p-value and see how unlikely is it that we would get a sample standard deviation or sample mean of that when we get a sample of size 37, and that's standard deviation and so on. So the sample mean, which is not equal to 5, and so that suggests maybe the alternative hypothesis is true. So to calculate the actual test statistic, the standardized test statistic. So this is what the sampling distribution, or really the t-distribution, will look like with 36 degrees of freedom. We're going to figure out what our t-test statistic is there, and then this is 2 tail, since we are going not equal to. So our t-test statistic will use this x bar 4.81 minus the mean of 5 divided by the standard deviation over root n. So that is our t-test statistic, negative 3.17. And so we put that on there, negative 3.17, and then find the area below it, and then also the area above it. And so if I was going to use the table, so the degrees of freedom is 37 minus 1, so it's 36 degrees of freedom. If I was going to use the table, I would have to look up positive for this positive number and find the area above and double it. And so that's going to get all kinds of weird here if we try and use our table. So let's do this. For 37 degrees of freedom, oh wait, there is no 37, so we go down to 30. And then we're looking for this negative 3.17, well, this is only the positive value, so we'll use a positive 3.17 and find that the area above positive 3.17 is between these two numbers, which means the area below negative 3.17 is also between those two numbers. So we use table B, degrees of freedom will go down to 30. It's between 0.001 and 0.0025. So then ultimately we need to double those two values and to know what it's actually between, because that's just one tail. We are supposed to do a two-tail test and find that probability. And so we double each of those, and so it's actually somewhere between 0.002 and 0.005. Ultimately, that's enough to make the conclusion. Our p-value is extremely tiny in this case, and so we have convincing evidence that it's not 5. But we'd really like to be a lot more accurate at that. So given the limitations of table B, our advice is to use technology to find the p-values when carrying out a significance test about a population mean. And so you can do this by if we want to find that above 0.317, we can do it in the calculator this way. This is going to be TCDF. And then we're going from, hold on a second here. All right, so I'm just going to show you this on the calculator because that slide had this screwed up. So we're going to go ultimately TCDF, so it's under second distribution. And then we've got T, not PDF, CDF. And then so lower bound, upper bound, really we want to go below negative 3.17. We can do that on our calculator. So I can go from negative 1E99 to negative 3.17. And then I have to specify the degrees of freedom, which in this case is 36. So we can do that and get our probability. But that's just one tail. Then we need to double it and get our actual probability there. So that is how we would go through and calculate a TCDF. And that was two-tail in particular. So let's see, switching back. That one's all wrong, but this one actually is right there. So they did from negative infinity up to negative 3.17, got that probability. All right, we'll continue in the next video.